Good to have everybody back. Now that we have a brand new mix of people, first hour is always going to be a little bit hard to wake up from. I understand that. So I'll try and be extra enthusiastic and exciting for you guys. How's that sound? So let's take a look at our question here before we try and remember where we were a month ago. Yes. So here's our question. A Hot Wheels car accelerates down a ramp. How do you find its average and final velocities? You have a meter stick and a stopwatch. So this is something that we would have done for a lab if we had some extra time. We're going to skip it because it's, when you come back after a month, it's best to just kind of review instead of do a big lab. So the way that you would do this, and the whole purpose of that lab would be to figure that out, is your average velocity is very easy. If you have a meter stick and a stopwatch, average velocity is just change in distance over change in time. So what that means is that you'd measure how long the ramp was, you'd time how long it took for the car to get from the top to the bottom, and you would just plug those numbers into the equation here. That would be your average velocity. In order to figure out the final velocity, that's a little bit more complicated. And that would take some time to try and figure out from the lab activity. Ultimately, where we would go with it would be this. One of the equations on your formula sheet is this. Average velocity is equal to original velocity plus final velocity divided by 2. So, if we wanted to solve for final velocity right here, and if we release that car at the top of the ramp from rest, that means this goes away, that's 0. So essentially, average velocity is equal to final velocity divided by 2. Therefore, in order to get your final velocity, you'd have to multiply both sides by 2. So your final velocity would just be 2 times whatever that average velocity is that you calculated earlier. So if you calculate average velocity to be 7, that means your final velocity, if you release that car from rest, would be 14. There's a summary of 40 minutes of a lab activity right there. Although we will do our best to work some Hot Wheels into physics over the next couple days. Questions on any of that? As though your brains are actually working already. I know they're not. I know mine's still slogging through this material. That's why today is a review day from the stuff that we've done so far. Hi, Martha. Thank you. You can sit anywhere. Okay, so to just kind of review some of the things that we've been doing, go ahead and get out a notebook or a piece of paper or something. If you don't have anything with you, maybe you're struggling like many people to just kind of get back in the swing of things. I'll grab some blank pieces of paper if that's something that you need.
Do you have like crayon paper?
What's that?
Is it like crayon paper that you have?
Yeah, I just have straight blank paper, no lines or anything. Who needs paper? Raise your hand. Okay.
Thank you.
You're welcome. One thing I'm excited about this semester is, last semester, teaching 4 different classes and having to record all 4 of them for remote students. I'm glad that 2 of those semester classes, are finished, so I don't have to record on 2 of them. But this is the one of the 2 classes I will be recording then over the course of the school day, so look forward to that. Alrighty, so remember we were doing things with graphs? Does that bring back a memory from last year at all? Okay. So that's kind of the main topic that we're dealing with in this chapter is position time graphs, velocity time graphs, and acceleration time graphs. Those three things are the key to actually doing well in this chapter. So we're just going to review some of those graphs, and we'll get as far as we can. Hopefully we get through all 6 today, and that'll be that. I would label the notes X/V/A versus T graphs. That's how I'd label it. So there's basically, if you want to proactively create these on your paper, we're going to do 6 examples that look like this. As you guys are, I know a lot of people might draw all these in right away. As we do that, anybody want to share anything fun about what happened over Christmas break at all?
2020 ended.
2020 ended. Nothing? My wife and I took, we were up in Oshkosh with our families for a couple weeks, and we took our little guy to Altitude. It's just like Sky Zone across the street there for a toddler day, and we bounced with him on the trampolines for a day. Oh my gosh, that was the most fun I have had in a long, long time. Man, I forgot how much fun you can have. And you guys ever been to one of those trampoline parks? Anybody? Oh my gosh, isn't that a blast? Just jumping super high, and I don't know what it's like across the road, but at Altitude they had these giant pits of foam balls, and you could just launch yourself into them. Oh my gosh, it was just great. I had such a fun time. I can't wait to go back there for another toddler day. Yes, I did several. The hardest thing when you jump into the foam balls is getting out, actually. Oh my gosh. So, I also figured out that one of the things is they have this like ninja course, which is really cool. And at the end, you would run up this thing like running up a wall. Then you grab on, then you'd have to fall into this big mat. And if you're ever doing that, and you're jumping into the thing where you fall off the big ledge off into, you want to hold your arms in. I had my arms out the first time I did that, and it scraped my elbow pretty good. So anyway, it was a really, really fun time, though. I had a blast. And if you ever get the chance to go to a trampoline park, do not turn it down. You will forget that you are a mature high school student, and you will turn into a kid from when you were just an adolescent, and it's a blast. Yeah?
Do we need any of the papers or notes from...
You should probably hang on to the velocity and acceleration notes from before. We'll also be diving into force diagrams eventually, too. So, well, I'm sure the folks at home were glad to hear that story. All right, let's jump into these graphs now. We'll start with a basic one here. So, let's say we have a graph that begins like this. And this is a position versus time graph. So, to just kind of think about what's going on here, this represents that at the beginning, the object is at the origin. So, if this is the origin here, this is the object, suppose I should hold it up for the folks at home. They would be beginning in the same spot. Now, as time goes on, you can see the position of the object gets further and further away from 0. So as time goes on, the shark's moving away from the origin. And that's what's happening here. And because this is a straight line, that basically means that it has a constant velocity. One of the things we talked about last year was what the slope of this graph means. The slope of a position time graph represents how fast you're going. It represents velocity. You don't have to memorize that. It's on your formula sheet. So, if that's what this graph looks like, the question is, what does the velocity time graph look like? And there's really two ways you can think of this. Number one, the shark is moving away with a constant speed. So we know that on the velocity time graph, the velocity is not going to be changing. And that would look something like this. As time goes on, this velocity remains whatever this value is. It does not change at all. So yeah, the easier way to think about this, and the way that I would advocate that you kind of think about these graphs, is just in terms of slopes. If this slope represents velocity, we've got a constant positive slope here. So that means we've got a constant positive velocity, which is what's represented right there. Now, remember, what does the slope of a velocity time graph represent? Anybody remember? Yeah, acceleration. So if this slope represents velocity, this slope represents acceleration. What's the slope here? 0. So my acceleration is going to be 0. The shark is not picking up speed. He's not slowing down. So he's got no acceleration. And that's that. Five to go. I think what I'll do is I'll go through the first 3, and then I'll give you guys some time to try and figure out the last 3. Admittedly, the first 3 will be the easiest. Alright, so here's the next graph. Doesn't it seem like it's been forever since we were in school? Oh my gosh. It feels so weird. I feel like I'm starting a brand new school year. Starting a new year, not a new school year. Anyway. So, you can see that at the beginning here, the object is starting away from the origin. So, as opposed to the previous example, where the shark began on the origin, now the shark starts away from the origin. And as time goes on, what happens? Does he get further away from the origin, or does he get closer? Closer, yeah. So it's like time begins right now. Time stops. So in this example, we're going towards the origin. When we're going towards the origin, is that a positive velocity or a negative velocity? Negative. So we've got a constant negative slope, which means we've got a constant negative velocity. For those two reasons, you can think of them either way. You can think of this as a negative slope, and that corresponds to a negative velocity, or you can just think of it in terms of the shark moving. It's moving towards the origin, so you know that's a negative velocity in and of itself. So, what's the slope here? 0. So our acceleration, once again, would be 0. Remember, before we went on break, we got far enough in this that these graphs eventually started to curve. instead of just being a straight line. And so we're going to take a look at some of those now too. Got ourselves a little half happy face right there. So the question might be, what does this represent in terms of the object's motion, and how do we fill in these other two graphs? So again, the easiest way to deal with these graphs is just thinking about their slopes. This slope represents velocity. We begin with a slope of about 0, right? So that means we're going to start with a velocity of about 0. As time goes on, you can see the slope increases. Therefore, as time goes on, the object's velocity is going to increase. Is it increasing in the positive direction or the negative direction? Positive, because it's a positive slope. So, maybe it would look something like this. Time begins right now. So it's like the shark begins at rest, and then he slowly picks up speed, going faster and faster and faster. That's what it would look like in that scenario. So, if my slope continually goes up, meaning my velocity continues to go up, this graph is going to show that. My velocity continually goes up, and you guys told me it goes up in the positive direction, which is why it's going up this way instead of down that way. What's my acceleration here? Positive, negative, or 0?
Positive.
Yeah, positive. It's a positive slope. Velocity time graph slope means acceleration. There you go. Three more examples. And these are all going to be curvy looking examples. Take, I don't know, a minute or two. See what you can do with this. Think about what's happening with the object and do your best to fill in the other two graphs. All right, so let's take a look at this together. What's happening here? Is the object starting from rest, or is it starting with a certain velocity? How can you tell it's starting from rest? Yeah. So slope represents velocity here. So we've got ourselves a flat slope, which means a slope of 0. Therefore, we begin with a velocity of 0. Are we starting at the origin or away? Away, because we're beginning up here. We're not beginning down there. So therefore, we know that if this is the origin, object begins away from it, and at the beginning, we have a velocity of 0. Now, as time goes on, that shark's velocity is going to grow and grow. It's going to get faster and faster. And we can tell that because this slope gets bigger and bigger and bigger. Now, it's getting bigger and bigger in the negative direction, but it's still getting larger and larger nonetheless. So the velocity is growing, but it's growing in the negative direction, which basically just means we're going to be moving towards the origin. And that's what would be happening here. So time begins, and then the shark goes faster and faster and faster, ultimately reaching the origin there. So, what is the velocity time graph going to look like here? Any guesses? Going down? Like this? I don't know, we'll see. Yes? Like horizontally? Yes?
Up towards the origin. We start at the bottom.
Up like this? All right. Anybody else have a guess for this one? Thank you for the participation. Wow, first day back on the first semester and first hour, and you guys are throwing up suggestions? That's great. So we've got 3 options here. We'll call this one A, we'll call this one B, we'll call this one C. One of these is correct. Anybody want to, well, let's just do a quick vote. Let's just see where everybody's at. How many people believe that, we'll do B first, the horizontal line. How many believe that's true? Okay. How about letter A, starting at 0, sloping down? That's quite a few. How about letter C, starting down, sloping up? That's pretty even. Okay. So we got to figure out which one of these 3 is correct. So I'll just start from A, then B and C. So for letter A, we begin with a velocity of 0. And as time goes on, that velocity is going to be growing. And it's growing in the negative direction. Is that what's going on here? Yeah. So letter A is correct here. Because we know that we start with a velocity of 0, because we begin with a slope of 0. Therefore, we can pretty quickly eliminate the others. For B and C, if you're beginning down here, you're automatically beginning with a negative velocity that's rather large, which would mean that over here your slope would have to start being pretty steep in the negative direction. Once again, thank you for your participation in that. That's great. So we've got ourselves that line right there. And the acceleration time graph. Is the acceleration positive, negative, or 0? Negative, because it's a negative slope. Very good. 2 to go. And a lot of time. That's good. Here's the next one. Same thing. See what you can do with it. It is nice to see you all again. I'm glad to have you back. This year in particular, the physics classes, you guys from last semester, all 3 classes really put in a lot of work, and a lot of people would participate, and you don't get that every year. So I really, really enjoy teaching you guys, so I'm looking forward to this semester. So, what's going on here? Is the shark beginning at rest, or is he beginning with the velocity?
With velocity?
Yes, with the velocity. How can you tell? Yeah, right away we've got that slope going upwards like that. Is he beginning from the origin or away? Yeah, beginning at the origin because we start at the 0 point. So, because slope represents velocity, we begin with that large positive velocity going away from the origin. As time goes on, our slope decreases, ultimately reaching nothing, which means that our velocity will eventually decrease, ultimately reaching nothing. So it's kind of like time begins right now. And he slows down. That wasn't very good. Let me try it again. Time begins right now. And then slowly he eventually comes to rest. So you begin with a fast speed, and then as time goes on, he slows down. So for velocity time, where should I begin? Top, bottom, or middle? Top. Because I start with a large positive velocity. As mentioned, this slope decreases, which means the velocity is going to decrease. So it's going to look something like this. Is that a positive, negative, or 0 acceleration? Negative, because it's a negative slope. So there you go. Boy, we only got one left, don't we? Yep, this will be the last one. Kind of. You'll see. It's all I had planned for today. There we go. That's our last one. So take another minute or so, see if you can fill out the other 2 graphs. All about the slopes. Now, because this is the last one, I'm going to need a lot of extra help here. So, first off, can somebody describe for me what's happening in this scenario with the shark and the origin?
Okay, so he starts away from the origin, he moves towards it at a quick speed, and eventually slows down until he gets to the origin.
Okay, so kind of like this. Sort of like that? Okay. Anybody want to give a different opinion? Anybody want to say they agree? Good. That's absolutely right. And we can tell that because we start with a big negative slope. And if we start with a big negative slope, that means we start with a big negative velocity. And all a negative velocity is it's a velocity that's going towards the origin. So yes, we start with a big velocity going towards the origin. As time goes on, that slope decreases, ultimately reaching 0, which means Sharky is eventually going to have a velocity of 0.
No. Okay. Okay.
What?
Because I think I got it right. But
Oh,
I'm
yeah?
not going to say it.
Okay. Well, we'll see when we fill out the other graphs then. So then, this velocity time graph, who can help me out on where we begin? Like up, down, middle, down? Oh. Why would I begin down here?
You start with a negative velocity in the position time graph. It goes down, which is negative velocity.
Exactly. We begin with a big negative slope here. And that means we're beginning with a big negative velocity, which is why we're going to start our velocity time graph down there. Now, where's this going to go? Is it going to go down, up, or straight across? Up. Very good. And the reason it's going to go up is simply because this is a velocity of 0. That's what that represents. So as our slope decreases, that basically means we're getting closer and closer to a velocity of 0. If I had a quarter every time I said the word slope today, I could spend the rest of the winter at the arcade across the street. So, as if they take quarters anymore. You guys ever been to Round One? Been there too. Another place that just makes me feel like a kid. Okay, the acceleration time graph. Is that top, bottom, or middle? Why?
Because as it's slowing down, its velocity increases. There'd be a positive acceleration.
Yes, yes. Because with this slope, there's slope again, with this slope, it's a positive one. And so if we've got a positive slope here, as Chip said, that represents acceleration. So positive slope on a velocity time graph means we have a positive acceleration. Okay. Nice job. And the cool part about all this is it doesn't get more complicated than this, aside from us combining a few of those graphs together. Now, that's the end of what I was going to do today. I'm also going to hand out the first gasp of the new semester.
No.
And guess what? You know how many pages this is? 1, 2, 3, 4, 5. Oh my gosh! A 5-page homework assignment.
Are you kidding?
So, here's how this is going to work. This homework assignment, basically, well, first let me just put your fears at rest. You're going to have the entire class period tomorrow to work on this.
Oh, okay.
And basically it's 5 examples like the 6 we did up here. Now, the only thing is, you got to pay attention to what's happening in the scenario. It specifically says, for those of you at home, it says whether or not the object begins from rest before it goes down the ramp, and it lists where the origin is. You can see it has 0, 25, and 50 on this picture. That means we're starting at the 0 point here, which would mean on this first example, you're starting at the origin. For an example like number 2, on this example, you can see 0 is down here, and then 25 is in the middle, and 50 would be up here. That just means you're starting away from the origin in this case, moving towards it. So you don't need to do anything with these numbers. They're just there so that you can see where the 0 point is, where the origin is. And that's really what this is all about. There's a couple different parts in here that might look tricky. I mean, look at this last example here. You've got one ramp, and then the ball would go on this flat part, and then it goes up the other way. The main thing you got to realize about this is any flat part of this ramp basically is a spot where the velocity is not going to change. That's all those mean. So, this should be fun to work through. And you'll have all of class tomorrow to work on this. And that's all she wrote. Any questions? Okay.